Okay, great. It's 4 o'clock, so let's start this webinar. So good afternoon or good day wherever you are. Thank you very much for joining the I²CNER seminar series. So I²CNER is short for the International Institute for Carbon Neutral Energy Research at Kyushu University. And this I²CNER seminar series was launched in 2010 upon the inception of I²CNER. Since then, this seminar series has featured a lot of many distinguished researchers around the world on carbon neutral energy research. And since the COVID-19, this seminar series has been held online. So I am Qing from the Faculty of Engineering at Kyushu University, and I am also a joint faculty of I²CNER. I am honored to be the host today. So today, I'd like to welcome Professor Qing Hao to give a lecture about how to manipulate thermal transport. So let me give a brief introduction of Professor Qing Hao. So Professor Qing Hao is a professor of the University of Arizona, and currently he is visiting Kyushu University as a JSPS fellow. Professor Qing Hao received his bachelor's degree in thermal engineering from Tsinghua University and obtained his master's degree from the University of Texas at Austin and his PhD degree from MIT in 2010 under the supervision of Professor Gang Chen. And he worked with Professor Gerd Sieder at MIT for postdoctoral research. And now he has worked on a variety of topics, including thermal transport inside batteries, power electronics, thermoelectrics, boiling and condensation, and many others. And he received many awards, including the IND 100 Award, AFOSR EAP Award, NSF Career Award, and so on. So because of the time difference, our director, Professor Petros Sophronis, is not here, and so Professor, I'd like to invite Professor Quota to give a few words. Professor Quota, will you give some words? Okay, no problem. And yeah, and before we begin, I would like to take a moment to remind you that your questions will be answered after the presentation. Please use the raise hand button or type your question and or comment in the Q&A box whenever you have a question. When you are called on, please unmute yourself and directly ask a question, or I will pick up some questions from the Q&A box. And this webinar will be recorded and made available on the I²CNER website and YouTube. Now, everyone, please welcome Professor Qing Hao. Professor Qing Hao, please start your lecture.
Okay. Yeah, thanks for the introduction. So this is actually my second time to Fukuoka, and I really enjoy my stay here. I'm Qing Hao from University of Arizona, and today's talk is about our thermal studies on nanoporous thin films. First of all, I want to talk about where I'm coming from. University of Arizona is located in Tucson, Arizona, the southwest part of the United States. So we are among the 62 major research universities in the Association of American University. And Tucson is famous for this very big cactus, which called saguaro, and this can really grow up to 12-meter height and to 150 years old. So which is amazing here. And Tucson is also one of the best locations to watch stars. So University of Arizona has been very strong in astronomy and optics research. So our research funding is leading the country in many categories for this type of researches. And the most recent work is the near-infrared camera for the James Webb Space Telescope launched last year. Just this week, we can see this full-color images sent back from the telescope. And right now, there's another giant telescope under construction at University of Arizona. So as we are looking into the sky, we also see potential growth for thermal science research in Arizona because we have a lot of heat here. To start my talk, I want to focus on this nanoporous thin films with periodic circular holes. The right side image basically is the temperature profile predicted by Phonon Monte Carlo simulations, where we can see along the heat transfer direction, heat is blocked by these nanopore edges. A better understanding of the heat transfer inside nanoporous silicon thin film involves a deeper understanding of heat transfer physics. In the undergraduate heat transfer textbook, we learned that in a semiconductor, heat are carried by free electrons and lattice vibration waves. So in quantum mechanics, lattice vibration energy is quantized, and the energy quantum is called a phonon, right? So phonon is basically the particle view of heat transfer. In this situation, actually the thermal transport inside the material can be viewed as phonon transport. So the image here is taken from our review paper, where we summarize the reported room temperature lattice thermal conductivity for different nanoporous silicon thin films. The x-axis is a mean beam length as a characteristic length of the structure. In radiation, the mean beam length is defined as 4 times the solid volume divided by the surface area of the nanopores. We also have two curves as theoretical prediction. The solid line is for 2D porous thin film with smooth top and bottom film surfaces. And the bottom curve is for a film with 22 nanometer thickness. This is the smallest thickness in all the measurements. And we assume the film surfaces to be very rough to diffusively scatter phonons, right? So in both cases, we assume rough pore edges to have diffusive phonon scattering. And we can see some data are within the prediction range, but some data can be much lower, right? So in theory, one hypothesis to explain the observed significant thermal conductivity reduction is based on the wave effect. If we consider heat as lattice vibration waves inside a periodic structure, the incoming wave and the wave reflected by periodic interfaces or boundaries may interfere. So we may have a phonon band gap in the phonon dispersion. Also reduce the phonon growth velocity, the thermal conductivity will be lower. In practice, this wave effect, also known as phononic effects, is anticipated to be weak because the feature sizes for nanoporous silicon thin films are usually much larger than the dominant phonon wavelength, which is on the order of 1 nanometer at room temperature. In addition, the pore edges are usually very rough. They will diffusively scatter phonons and destroy the phonon phase coherence. So in this case, we may have this incoherent phonon transport. And in some calculation, it has been suggested that the phononic effect can be neglected for feature sizes larger than 100 nanometer. So the second hypothesis is based on the pore edge defects, such as amorphization and oxidation. This was first proposed by molecular dynamics simulations. In real samples, for the TM image, we can see this 1 to 2 nanometer pore edge surface layer, right? The existence of pore edge defects would effectively expand the nanopore diameter and lower the thermal conductivity. So in measurements, there are different ways to justify the importance of phononic effects. One simple way is to compare the thermal conductivity between periodic and aperiodic patterns, because wave effect requires periodic patterns, and we should see some difference between the two cases if the phononic effect is dominant, right? So the comparison studies by several groups actually suggest that phononic effects can only be important at about 10 Kelvin or lower. The second approach to justify the phononic effects is to measure the specific heat, right? In theory, the specific heat only depends on the phonon dispersion. If we have very strong phononic effect, the specific heat will be very different from the bulk material. And this is our measurement for the focus ion beam drilled nanoporous silicon thin film. And the symbols are the measurement data. The band, the green band, is our prediction using the bulk specific heat properties. So all the specific values are normalized by 1 minus porosity. So we can see the measured specific heat of nanoporous silicon thin film basically follow the predictions based on the bulk values, right? So this basically suggests there's a negligible phononic effects inside these films. And in a more recent study, we proposed a new way to justify the phononic effect, basically just by checking the thermal resistance change of a silicon thin film with an increased number of rows for nanopores. So we can find some analogy in optics. For example, in Bragg refractor, if we consider wave effect, the transmittance across this periodic structure would saturate beyond a certain number of layers. If we consider particles, the retracing method will suggest continuously decaying transmittance across the structure because each interface would scatter the light, right? So we can extend this idea to heat conduction for 1D superlattice thin film. So in this case, if we have very strong wave effect, phonons would actually view the whole thin film as a homogeneous medium, right? And the phonon path will be largely restricted by the thickness of the thin film. In this case, the thermal conductivity will become a linear function of the number of periods or layers. And the cross-plane thermal resistance defined as a ratio between the thickness of the film divided by thermal conductivity will become a constant, right? Basically, it will saturate. And when we extend this 1D superlattice thin film to a 2-dimensional nanoporous thin film, basically the number of layers is in analogy to the rows of nanopores. So to do our measurement, we actually use the so-called T-Junction measurement technique, which was proposed by Professor Xing Zhang when he was working at Qing University. So the SEM image here shows our setup. We have a long beam, and in the center of the long beam is connected to a short beam as our measured sample. So in the long beam, we actually deposit a metal line as both a heater and thermometer. For electrical insulation, we coat both beams with 34 nanometer silicon nitride. We should note that here the long beam and short beams are fabricated from the same silicon film on an SOI wafer, so there is no thermal contact problem. So in the measurement, we pass a DC current to heat up the long beam, and the average temperature rise along the long beam can be measured from the electrical resistance increase of the metal line heater. In the measurement, we can increase the number of holes in the center of the short beam with a focused ion beam, right? After all the measurements, we are going to cut the short beam with a focused ion beam and redo the self-heating measurement for the long beam alone. the contrast between the measurement with and without the short beam will give us the short beam thermal resistance or conductance. So here we did a measurement with a pitch of nanopores of around 250 to 270 nanometer. And if we check the TEM image, we have the gallium nitride as red dots around the nanopore edges, right? So this will basically expand the effective diameter of the nanopores to around 160 nanometer. So if we plot the resistance of the short beam as a function of the number of rows for nanopores, we can see the resistance basically increase almost linearly here. So that basically suggests there's no phononic effects, because if you have very strong wave effect, the resistance should saturate, right? Also, all the measurement data as a symbol here can be explained with a dashed line as a Phonon Monte Carlo simulation using this effective pore diameter, right? So basically here we find out for our measured temperature range, we don't have very strong phononic effects. If we want to see those kind of effects, we have to go to very low temperature, okay, or very small structure size. As a second topic, I want to draw your attention to a new nanopores pattern, which is a periodic nanoslots. So the heat transfer inside nanoslot pattern silicon thin film usually involves the so-called ballistic thermal resistance, which happens when the phonon is passing through a geometry constriction. For example, the contact between a nanowire and the substrate. If the size of the contact is much smaller than the phonon mean phase path in the substrate, phonon will radiate into the substrate to a distance on the order of the phonon mean phase path. So in this regime, we wouldn't see any temperature gradient. Compared to the case predicted by the Freese law with the temperature gradient, the ballistic transport will largely reduce the heat transfer, right? So that basically introduce an effective thermal resistance called ballistic thermal resistance to block the heat transfer. In practice, we see this ballistic thermal resistance in many applications. For example, we can see phonons emitted from the tens of nanometer hotspot inside a power electronic device, right? So the heat transfer is blocked by the ballistic resistance. We can also see ballistic resistance for phonon passing through the neck width between two adjacent nanoslots. And for 2D materials such as graphene, we can pattern this periodic nanoslot and use a small neck width to restrict the thermal conductivity. And for thermoelectrics, if this neck width W, right, which is here, is smaller than majority phonon mean phase passes, but still longer than the electron mean phase path, we can largely reduce the thermal conductivity, but still keep bulk-like electrical properties. So this will benefit thermoelectric applications. And I should point out that this nanoslot pattern can be applied to general 2D materials and thin films to tune the thermal conductivity. And in theory, we have developed some simple but accurate analytic model to predict the lattice thermal conductivities for nanoslot pattern thin films. First, we can calculate the characteristic length LC based on the geometry of the thin film. And this LC will be used to modify the in-plane phonon mean phase path inside the thin film. And the obtained lambda effective will be plugged into the kinetic relationship to calculate the thermal conductivity. Here, C is the phonon specific heat, Vg is the phonon group velocity, HW is a correction factor, accounts for the reduced cross-section area inside the power structure. And we can calculate HW based on the Freese loss analysis as the thermal conductivity of the power structure over the solid film. HW is also used in the LC calculation here. So if we follow this idea, when we change the W value, we can modify the phonon mean phase path and change the thermal conductivity. For fundamental studies, we can actually use this to extract the Phononic path distribution inside a thin film. In virtual measurement, we use Phonon Monte Carlo simulations to simulate the thermal resistance of a thin film with different W values for the nanoslot pattern. And we can use those data points to reconstruct the Phononic path distribution, basically the so-called accumulated thermal quantity. And this accumulated thermal quantity is a percentage of the thermal quantity that is contributed by phonons with Miffy path from 0 to any lambda value, right? When this lambda naught goes to infinity, we have 100% of the thermal quantity back up. So this is for fundamental study. And we propose our idea, but we didn't do measurement. And Professor Nomura's group at the University of Tokyo actually carried out the measurement using our approach for a thin film with 145 nanometer at 3 different temperatures here. So more recently, we also did some measurement for nanoslot patterned silicon thin film. And our focus right now is shifted to further reducing the thermal quantity simply by offset the adjacent rows of nanoslot, right? So in the left image, I'm showing you the heat flux intensity distribution. We can see that in this offset nanoslot pattern, basic heat conduction is along some zigzag channels. We have certain regions with very small heat flux, right? So those regions are inactive heat conduction. They are basically called thermally dead volume by Cancellation. And one advantage for nanoslot pattern is that we can not only change the thermal quantity, but also change the thermal anisotropy, right? Basically, the thermal quantity is not isotropic along the 2 directions, perpendicular to nanoslot or along the nanoslot direction. And so this will give us a lot of flexibility in thermal designs for the thin film. As I mentioned earlier, nanoslot pattern can also be used to benefit thermoelectric applications. For thermoelectrics, we are looking for a higher ZT value for the material, and the ZT is defined as the Seebeck coefficient square times the electrical conductivity times the absolute temperature and divided by thermal conductivity. If the nanoslot pattern has a characteristic length much smaller than the phonon Miffy path, but still longer than electron Miffy path, this K value will be largely reduced and ZT will be higher than the solid thin film. So in this figure, I'm showing the ZT as a function of temperature for different nanoslot patterns for the thin film. In comparison to the values, ZT values for nano-grained bulk silicon, right? We can see with a small W value as 5 nanometer, our result is basically comparable to the best bulk values using nano-grained bulk silicon. But I should point out here that we only use the nanostructure to reduce the thermal quantity. In many cases, like experimentally measured bulk materials, they have more defects to further lower thermal quantity and benefit ZT values. So in applications, more recently, we actually extend our research to 2D thermal cloaking to make an object thermally invisible as the thermal counterpart of optical thermal cloak, right? So there has been a lot of papers in the last 10 years for this topic. So the common way to achieve the thermal cloaking is to coat your protected region with a shell region, right? In one simple thermal design, the thermal quantity of the shell K2 and the thermal quantity of the background medium KB, their ratio is determined by the geometry, basically the inner and outer diameter of your shell region. This bulk composite design works pretty well for bulk materials. However, at nanoscales, it's not easy to use because at small scales, the interfacial thermal resistance becomes dominant and it's hard to control the resistance in experiment, right? So we just think about this problem. We think we can actually use nanoporous pattern to pattern the nanoholes in the background medium region and lower the Kb value and to get our desired Kb-K2 ratio, right? So here is the temperature profile given by Phonon Monte Carlo simulations. We can see the temperature profile is largely similar to the profile given by Friis analysis for the bulk composite design, right? Using the same K2 and Kb ratio. And I should point out this nanoslot pattern can be widely used across the thin film to locally change the thermal properties. So we can actually design even more complicated structures for different applications. If you have more interest, you can see more discussions in our paper here. And as a last topic, I want to talk about some recent studies for convection study for nanoporous thin film, right? And this could be used for the device cooling application. And here we basically carry out a 3 omega measurement on a metal-coated nanoslot pattern silicon thin film. The SEM image is given here. So when you do the 3 omega measurement in vacuum and in air, and you can do some data analysis to extract the heat transfer coefficient H on the surface of the sample. And for sample of this micrometer size and nanometer thickness, air conduction will be dominant, and the bulk convection is usually neglected for heat dissipation. So in the literature, the typical model to predict the heat transfer coefficient for nanostructures is called the two-layer model. And this is from Professor Xinzhang's group at Tsinghua University. So in the two-layer model, we consider a non-continuum layer close to the surface of the sample. The layer thickness is on the order of the air molecule mean free path, right? So air molecule would have a ballistic transport inside this layer. Outside the layer, we have this continuum layer with bulk air conduction, right? So this model was initially developed for the nanotube and nanowire patterns, right? So in our study, we found out the two-layer model can actually be extended to general geometries if we use the mean length of the structure to replace the equivalent diameter of the nanotube, right, in the model. So here I'm showing the comparison between the two-layer model and all the measurement results in the literature. Some are for wires, some for tubes, and some are for thin film and cantilever, right? For our nanoporous thin film, we can find out the data here. So in general, our data agrees very well with the two-layer model prediction. And one interesting thing is that the two-layer model actually predicts the peak heat flux, which is close to 1.1 10 to the fifth power at equivalent nanowire diameter of 10 nanometers. This is a very high value compared to the bulk convection, right? So we can think about this as potential applications for device cooling using nanoporous structural nanowires. So in summary, we did this periodic nanoporous film study. We found out different ways to justify the phonon coherence. In the recent study, we basically just check the thermal resistance change of the thin film with increased rows of nanopores, right? So we find out that the phononic effects are not important in our measured temperature range. So if we still want to see those effects, we have to go to a much lower temperature. And we also extend our study to periodic nanoslots as a new nanoporous pattern. And this pattern can give us more flexibility in reducing the thermal conductivity and changing the thermal anisotropy, right? So in the future, we can also measure ZT values for those films. And for thermal management, we think about thermal cloaking and cooling applications for nanoporous silicon thin films. At the end, I would like to acknowledge the contribution from my previous students and postdocs and funding support from National Science Foundation. Right now, I finished a little bit earlier, so here I want to give a short advertisement for our own journals. As you can see, some of the papers are actually published on ESMM, right? So we have several journals under this engineering science publisher. So our flagship journal, Engineering Science, right now has a set score of 16.6, right? Which basically ranks among the top 6% in all the categories. And ESMM is also Scopus Index and will receive its first set score later this year. And both journals are under SCI evaluation for now. So if you have some interesting paper, please do consider our journals. And we should be able to advocate your work heavily in the society. Okay. So with that, I want to conclude my presentation today. So I will be glad to take questions.
Okay, thank you very much, Professor Hao. Let's move on to the question and answer session. So if you have any question, please raise your hand and unmute yourself. Okay, please unmute Takuma Sensei.
Okay, can you hear me?
Yeah, no problem.
Okay, thank you. This is Takuma from Tokyo University of Agriculture and Technology. Thanks for your great talk, because indeed I always cite your paper when I publish. So
thank you.
Could you show me the slide on the nanothread?
Nano what?
Nanothread. You explained that we need to modify the thermal conductivity by Fourier analysis in your slide. Can you show the slide?
You mean the Nanoslot pattern slide?
This
one? This one?
The previous one, maybe on 3 or 4.
The previous. This one? Let me see.
You just react this page. You use this HW, right?
Yeah.
So I'm curious on of course we need to modify this and using this correction factor, but do you have any idea? We must use the Fourier law analysis, but do you have any alternative idea not to use this Fourier law analysis, because it's really not I'll say comfortable for us to use Fourier law analysis and point transformation. It's very not good for us. So we need to omit this. But do you have any idea to do so?
I think, of course, there are people doing some machine learning, which is even more complicated to predict HW value. My student actually just make a simple table and interpolate in the table, right?
I see.
To give a rough estimation. Because the Nanoporous pattern can actually be random, right? So there's really no general way to quickly predict HW, particularly if you talk about some strange shape, irregular shape for nanoholes, right?
Yeah, there is some models to represent this HW, but do you have any paper who validates such kind of models?
I don't have but I just say other papers, they always use console to do simulation. Maybe there's some free software you can find out on the website to do the simulation. I think because my student just use interpolation to quickly estimate, usually the error is not too big.
I see.
If you can make a large table with enough data, you can interpolate.
Okay, thanks for your idea.
Yeah.
Okay, thank you. Any other questions? Kono Sensei, please.
Do you hear me?
Yeah.
Thank you very much for very exciting presentation. I have a question about your thermoelectric.
Mhm.
So you reduce the size of the film. You use a thin film to reduce the thermal conductivities.
Yeah.
And I'd like to know how that kind of the reduce of the size affects to the Zebek or electrical conductivities.
Reduce the size if your feature size is still much longer than the electron mean-free path, and electron quantity will be bulk like electron conductivity. So it just if the size is even smaller than electron mean-free path, electron quantity will be decaying, right? And seeback coefficient usually depends on the scattering, and unless you really reduce the size to very small, I don't see a change for seeback value.
Okay, so in your case, you can reduce only the thermal conductivity and then enhance the ZT.
So because the phonons has much longer mean-free path here, right? So when you reduce the size, the phonons will be effective first, right? Before electrons will be scattered by the pore edges, right? So so this K will reduce much more than possible reduction for sigma because electron has much shorter mean-free path, right? This is generally true for heavily doped semiconductors because electrons usually have much shorter mean-free path than some of the phonons.
Okay, thank you very much.
Yeah, thank you.
Okay, thank you very much. Is there any other questions? Okay. Okay, please, Professor Gargate, please unmute.
Thank you, sir. Hear me?
Yeah.
Okay. So my question is regarding related to the pore diameter. If the pore diameter is higher, what will be the effect of phonic on heat transfer?
Effect of what? Which slide you refer to? Or general the pore diameter?
Yeah.
Let me see the. So you say if the pore diameter is larger, what will happen?
Yeah. Phonic effect.
Oh, that one we didn't consider those kind of effects yet. I know some of the paper from University of Tokyo, right? So right now we just do our measurement, and for the measurement for the samples we measured here, basically we will see agreement between Monte Carlo simulations and the measurement results. Right? If you really change the size to some extreme case, we may consider additional effects here.
So my next question is, it is the nature of nanoparticles will affect the phonic effect, like we have nanoparticles amorphous and crystalline in nature. So it should be a crystalline in nature for the study of phonic effect.
Phononic effects really requires the very smooth pore edges, because if you have this rough pore edge, phonons will be diffusively scattered, and that diffusive phonon scattering will actually randomize the phonon phase, and you will never have coherent phonon transport in that case. So people can see some superlattice with a structure size as 5 nanometer. You can see some wave effects. And superlattice has atomic level smooth interfaces, right? So that's why you can see it. But for those nanofabricated nanopores, usually the pore edge is more like it's rougher, right? It's rougher, so you may have more diffusive phonon scatter to kill this possible phononic effect. So we are also doing some annealing studies to possibly change pore edges and make it smoother, see whether we can see phononic effects at higher temperature, right? So, but nanofabrication, usually when you etch the nanopores, the pore edge is usually rough to largely kill the phononic effects. Yeah, I'm not sure whether that answers your question. Yeah.
Yes, sir. It means crystalline nature is required for the coating surface. The
crystal nature smooth surface for the nanopores. Yeah, those are usually preferred to have the strong Phononic effects, particularly at higher temperatures.
Okay. Thank you, sir.
Okay, thank you. Any other question? Oh, any other questions? Okay, Mr. Ni Dawei, please.
Okay, thank you for presentation, Professor Hao. Could you please turn to the page you showed the ZT value for formation for
Yeah.
formula?
ZT value, okay.
Yes.
Okay, here.
Yes. I know that Professor Dresser-Haus proposed that the nanoscale confinement can be used to enhance the ZT value. And however, in this in the nanoscale confinement, the nanoscale confinement will also reduce the mean free pace of the electron.
Yeah.
Not only the phonon. So maybe in this work, it is difficult to estimate the size effect on the mean free pace of the electron.
I mean, we in our calculation, we already consider the size effects for the electrons. We have the electron mean free path, and we also have the structure size to modify electron mean free path. But because the electron mean free path is generally much shorter than the phonon mean free path, their impact on electron mean free path is actually very weak. So the model we already modify this sigma, but just that modification doesn't have a very big influence because the mean free path of electrons is much shorter.
Okay. Thank you so much.
Yeah.
Thank you very much.
Any other questions? Yeah, we still have a lot of time. So if you have any question, please feel free to ask Professor Hao. Okay. Professor Roman, please.
Can you hear me?
Yeah.
Hello, this is Roman Anupria from the University of Tokyo. We are here also big fans of your work on the nanoslits. I was wondering about new publication where you speak about the anisotropy of the slit pattern. It looks like you simulated fairly small, like pattern, right? Like theoretically, I mean. And I was wondering, like, how large? I mean, this effect might be present when the nanoslits are very small, but like experimentally, how large do you think could be the slit pattern to still observe it experimentally?
I mean, this is actually our measured nanoslot pattern. We do the same, right? So of course, if you think about ideal nanoslot, you think about 5 or 10 nanometer, which is hard to be fabricated on the thin film. But this is what we actually fabricated this pattern, right? And we do the simulation. And usually, if your nanoslot has a certain depth here, and you just add this additional this nanowire region, right, to add some thermal resistance. So basically, heat has to be passing this nanowire region first, and then go to another part of the structure, right? So the addition to adding those nanowire region doesn't change the major heat transfer in the rest of the regions. So I'm not sure whether I answered the question. I'm just saying that if you have a nanoslot pattern here, right, and if this one has a certain depth, this B value is large, right? The B value is large due to fabrication limitation. And that will just add this rectangular nanowire region as additional thermal resistance to the whole structure. But outside this neck region, this region, and your predicted temperature profile will be the same, right?
Right. Yeah.
Right. So this is just, you can view this part as a nanowire, right? This B is the length of the nanowire. So if B is expanded, you just got a longer nanowire to connect the left region and right region. right? But in these two regions, the ballistic resistance calculation is still the same, right? You just consider you got the ballistic resistance here, right? When phonons are emitted to the left region, ballistic resistance here when phonons are emitted to the right region, and you have this nanowire thermal resistance added to the structure.
Yeah, but like it also, I mean, it would depend what kind of thermal conductivity you're probing, if it's effective thermal conductivity or it's like, or this ballistic resistance is actually taking into account.
Yeah, ballistic resistance doesn't depend on the B value, because the ballistic resistance is when phonons are coming out of this geometry constriction region, right, into this left and right space, right? So if you increase the B value, ballistic resistance is not affected. Ballistic resistance only depends on the W value.
Yeah, okay.
Right.
Sure.
Of course, this is a very, very important aspect for nanofabrication, right? And of course, if B is very small, and that's the ideal case, your whole analysis is very simple, right? If B is large, you have to consider those nanowire regions.
Okay, thank you. I guess we'll discuss when you visit the University of Tokyo.
Yeah, we can discuss more. I'll be there later this month.
Okay, thank you for the talk.
Sure.
Okay, thank you very much, Professor Roman. And is there any other questions? So if you have any question, please feel free to ask Professor Hao. Maybe the phone is a little bit difficult for the students. Yeah. And so Professor Hao, will you share some application scenarios of this kind of thermal transport manipulation?
I mean, for example, in the semiconductor devices, right, if you have a hot region and close to that hot region, you have another very fragile device. So you may do some thermal cloaking to protect that device from the nearby heating source, right? Yeah. And that could be a simple application. And also I mentioned the cooling application, possible cooling using nanoporous silicon thin film, because it has a very large surface volume ratio, right? So you can think about, you can dissipate more heat out of the device. And right now we know that device cooling is the major bottleneck for the high power electronics, right? So there are a lot of things we can think about. And beyond that, thermal electrics is still useful for certain device cooling applications, and we can integrate those nanofilms with other silicon devices, because they could be fabricated from the same device layer, right? And that could be another consideration, right? And mostly we consider cooling protection. Of course, you can also do some other, University of Tokyo and Professor Nomura, they did a lot of things for thermal focusing and other stuff. And also Professor Baowen Li is doing this phononic computer idea, right? You think about thermal diode and you think about other counterparts as electronic devices, right? If you have an electronic diode, you want a thermal diode, right? So something like that. And this kind of patterns could be used for those kind of applications as well, right?
Okay. Thank you very much. So is there any other questions? Actually, I am also interested in the fabrication process. So can you compare some state-of-the-art fabrication techniques for this kind of course?
The state-of-the-art fabrication for the EBL, electron beam lithography, you can define sub 10 nanometer pattern, right? Yeah. But you can define that pattern doesn't mean you can fabricate those small holes across the silicon thin film, because usually there is a aspect ratio restriction for dry etching, right? When you etch a hole, the diameter and the depth of the hole, the ratio cannot be, you cannot have very high aspect ratio for the hole. Usually it's 3. So if you got the thickness of the film like 70 nanometers, the smallest pore size will be 20 or something nanometer, right? And in reality, my students usually do 1 by 1, so they don't do very high aspect ratio etching. Maybe some group can do 1 to 3, right? So you can do a smaller hole compared with the silicon thin film. So basically, this pattern is not only restricted by the feature size given by electron beam lithography, but also be restricted by the dry etching aspect ratio for the nanopores, right? Of course, if you think about the ultra-fine silicon thin films, or if you think about 2D materials, and you are not restricted by this aspect ratio, right? Then in that case, for graphene, you can actually pattern the smallest size given by electron beam lithography, or you can directly use electrons to drill holes on graphene. That could be the smallest size you can achieve.
Yeah, thank you very much for your insightful opinions. So if there are any other questions? Yeah. If there's no further questions, yeah, we have a really fruitful webinar today. We have a 30 minutes lecture, and we have discussed for about 20 minutes. So I'd like to thank Professor Qing Hao again, and thank you very much for your wonderful lecture. And if there's no further questions, I'd like to close this webinar. Thank you very much. Thank you all the attendees.
Okay, thanks for the opportunity. If you have more questions, you feel free to basically send me email to ask a question. We can communicate by email as well. So I will be in Kyushu University until August, so students can just visit my office here to discuss.
Yeah, and I want to remind you that today's webinar will be also put on YouTube and the I²CNER website, so you can review today's webinar later. Okay, thank you very much. Thank you.
Okay, thanks everyone. Bye.
Bye.